So now that you know what goes in to pick out a proper internal standard, we need to now take a look at the data. What are we to expect when we run these standards? All right, so first off, we're going to kind of make up an example as we go. And I've created an internal standard set. So I've got 4 volumetric flask, 1, 2, 3, and 4. And I'm just going to make this easy. It's going to be a 1 part per million, a 2, a 3, and a 4 part per million. And then the internal standard has went into each flask. And remember, it's the same amount for every single one. And then I'm going to turn around and I'm going to do a set of 3 samples. So we're analyzing 3 samples. And I'm going to call this S1 and S2 and S3. And then in each one of those, I have put in the same amount of internal standard. How much of it? We're not really focused on that right now. We need to walk through the theory first. So I'm going to take all of these to an auto sampler tray. 1, 2, 3, 4, 5, 6, and 7. 1 through 7. I've loaded up my standards. I've loaded up my samples. And I've went to a GC instrument, gas chromatography. And a GC auto sampler uses a needle, and that needle is going to puncture into each one of these vials, and it's going to shoot a sample into the machine, and we're going to get data. All right, well, this is a standard and an internal standard. So what should happen here is that I should get a signal for the standard that I have used, right? And I should also get a signal for the internal standard that I have also used. So each standard should have 2 positive signals. Okay, well, going back to a previous example, let's say that we are analyzing benzene in gasoline. All right, so benzene is a 6-membered ring with a couple of double bonds on the inside. And let's say we don't do gasoline. That's too complicated. To pick out an internal standard that's not going to be present in gasoline, that's going to be pretty difficult. All right? The standard addition process would work much better for that. So let's say that we pick out benzene in a vitamin C soft drink. All right, so I'm analyzing for benzene and I need an internal standard. An internal standard, we said, is going to be basically a something that's very similar that's probably not going to be found at all. So I'm going to pick out toluene as the internal standard. It's very similar to benzene. There's a few modifications on it, but they're pretty close, right? And I shouldn't find toluene in a drink, but there are reports that have shown benzene present in vitamin C drinks. Okay, so I go to the GC system, I'll run all of these standards, and what will happen is that I will get 2 positive signals from the instrument. One signal will come from maybe the internal standard or the standard, and here I'm going to put standard, and the other one is going to come from the internal standard. I know there's 2 things present. I put both of those things in my standard, right? One represents the benzene that I have put in there. One represents the internal standard that I have put in there. And I've analyzed it, and I've gotten data from the equipment. All right, well, this is standard number 1. Well, what if I run standard number 2? Should I expect to see something different? And the answer is yeah, we should expect to see something different. Because in standard number 2, I have put in more benzene, so that benzene peak should go a little bit higher. But you know what? My internal standard stays the same. And the reason is because I have put in the same amount of internal standard in every single one of them. So here's my benzene peak. My benzene peak now, my standard is higher, and it should be. There's more in it. And then here's my internal standard peak. And this should be about the same amount for every single one of them. So when I run standard 3, the benzene would go even higher, but my internal standard will still stay the same. Standard 4, it would go even higher, but again, my internal standard will stay the same. So I'm going to start generating some data. Standard number 1, 2, 3, and 4. And this is my benzene area. And this is going to be my internal standard area. Well, the benzene area will increase. That's what it's always done. Every time you've made a calibration set, you've put more and more and more standard into them, which gives you more and more and more area or more signal. So let's say that this starts off to be 50, and then it goes to 100, and then it goes to 150, and then it goes to 200. Again, I'm rounding it off. The internal standard, though, this area should stay equivalent. And the reason is because I have put in the same amount every single time. So let's say that this one turns out to be a 5. Here we have a 4.9, a 5.1, and a 5.3. They're all pretty close. And that's what I would see traditionally in some type of laboratory data. They're going to be close. They will not be perfect. They never will be perfect. They never will be an identical area or a signal associated with them. And the reason is because my equipment is not that good, right? I'm relying on my injection needle to inject the same identical amount every single time, and it's not going to happen. I'm relying on that sample to come through the same way every single time it comes through. I'm relying on the detector of the machine to see everything in that sample so it can report it to me on a sheet of paper, and that's not going to happen the same way every single time. So there's too many variables, too many variations that can happen. So they're going to be close, but they will not be exact. And this is one of the things that I look for. Because if they are not close, then that means one of these standards, well, too much of it was injected or too little of it was injected. But the internal standard is going to make my math a little bit easier. It's going to make it a little bit better. I don't have to rerun them. I don't have to reanalyze them. I just have to algebraically modify the number to bring it back on scale. All right, so this is the data that you will start generating from your standards. Standards 1 through 4, areas from your analyte, and areas from your internal standard. But if someone asked you to plot a calibration curve using the internal standard, you just simply don't do standard 1, 2, 3, 4. Let's say that these are part per million. 1 part per million, 2, 3, 4 part per million, and plot the benzene area on the curve, right? Why would you go through injecting the internal standard if that was the case? That's a normal calibration curve. That's how we started out the semester, right? But now this is a better method. So how do I incorporate the internal standard when I make my calibration curve? How do I solve for these little weird things that might happen throughout my analysis? Well, I'm going to create a third column over here. And this third column is what I'm going to call the ratio. And this is how you handle it. We know that the internal areas should all be the same. We also know that if more internal standard was injected, more sample was injected. If less internal standard was injected, less sample was injected. Because ideally, they should all be the same value. So what I do is that I create a ratio, and I take the area of my analyte, 50, divided by the area of my internal standard, which is 5.0, and I get a number. And then I do the same thing for the next one. I take 100 divided by 4.9, 150 divided by 5.1, and then 200 divided by 5.3. So I take the area from the analyte divided by the area of the internal standard, and I get this new ratio that begins to get developed. If one goes up, the other one should go up. If one goes down, the other one should go down. And this ratio helps neutralize all of those changes that might happen throughout the analysis. So on the calibration curve, what would happen is that on the x-axis, I would plot the ratio, I would still plot the concentration like we've always done. So concentration goes on the x-axis. 1, 2, 3, and 4. That's what I made. Those were my standards. That's the concentration that they should have been. On the y-axis, up and down, this typically was given to signal. But we have two signals here. One from my analyte, one from my internal standard. Well, I can't have two y-axes. What we've done is that we've created a ratio. And this ratio is the important one. So the ratio goes on the y-axis. And what you hopefully would end up with is still a straight line. So that is how we plot a calibration curve using an internal standard. Look at the areas from the thing that you're making a standard with. Look at the areas of the internal standard. Divide the two. Get a ratio. And this time, you plot the concentration on the x like always, and you plot the ratio on the y-axis. Now, what about my samples? Well, the samples will also have two components, right? Or more than two. The samples could be a complicated mixture. So I could see a big benzene peak and then an internal standard peak, and then maybe some other things out here on the end that I'm not worried about. I don't really care about those. Here is the benzene peak. There is the internal standard peak. So I would get a number for the analyte. I would get a number for the internal standard, and I would do the same thing. I would divide the two. Take the area of the analyte, divide it by the area of the internal standard, and get a value. You still do a y equals mx plus b. The x concentration is going to be typically what you solve for. The y is going to represent the ratio, which means that you need to take this value, this ratio, and plug it into the y-axis. Just like before, we're not changing anything at all on you except the idea of using a ratio now instead of the strict areas that come from the data and from the chromatograms or from the report that you're running. That's the only thing that we're doing. So if I do the ratios for the standards, I have to do ratios for the samples, which means internal standards have to be carried all the way through. They have to be present in all standards. They have to be present in all samples. You have to do the ratios for the standards. You have to do the ratios for the samples. If you don't have a proper number to plug into the linear regression line. Okay? So that gets you started in the direction of understanding how to handle this mathematically and algebraically as far as generating a calibration curve and figuring out what to do with the data from the reports. So in the next video, we'll continue on with these examples. We'll continue on with the idea of an internal standard, and you might see some actual numbers integrated within an example problem.